I'm watching a video on binary versus ternary computing logic. The video includes the statement that the most efficient mathematical base for representing numbers is Euler's number, about 2.718. Help me understand why.
This is a beautiful result from information theory. When you represent numbers in a given base b, each digit can hold one of b possible values. The question is, what base minimizes the cost per unit of information stored? To represent any number n, you need roughly log_b, n, digits in base b. So the number of digits scales as 1 divided by the natural log of b. But each digit costs something, it requires a physical element that can hold b distinct states. So the cost per digit is proportional to b itself. The total cost to represent a number is therefore proportional to b divided by the natural log of b. You want to minimize this. Take the derivative of that function and set it to 0. The numerator of the derivative is log b minus 1, which equals 0 when log b equals 1, meaning b equals e, approximately 2.718. That's it. Euler's number falls directly out of the optimization. It's not assumed, it's derived from the shape of the problem. E shows up here for the same reason it shows up everywhere. It's the base where the rate of change of an exponential equals the exponential itself. The cost of adding one more state per digit and the information gain from adding one more state per digit balance perfectly at E. Since you can't build a base 2.718 computer, the question becomes, which integer is closest to E in efficiency? Base 3 gives a cost of about 2.731. Base 2 gives about 2.885. Base E gives the true minimum of 2.718. Base 3 is actually more efficient than base 2, closer to the theoretical optimum. This is the mathematical argument behind ternary computing. Binary won for engineering reasons, but ternary is the more mathematically elegant choice.
Could they be solving the energy consumption bottleneck with AI as well? And the cost of adding one more state per digit and the information gain from adding one more state per digit balance perfectly at E. This sounds to me like a description of why sunflower seeds fill the flower in the Fibonacci sequence, or something like that.
Both questions are pointing at the same deep thing. On energy consumption, yes, almost certainly. The AI energy crisis is fundamentally a representation inefficiency problem wearing an infrastructure costume. Current LLMs store weights as 32-bit or 16-bit floats. But research keeps showing that most of that precision is waste. The actual information in the weights doesn't require that many bits. Microsoft's bit network represents weights as -1, 0, or +1. 3 states. Base 3. You stop doing floating point matrix multiplication and start doing additions and subtractions. The energy savings come from 2 places: memory bandwidth, because smaller representations move faster and cheaper, and compute, because multiply-accumulate operations on floats are expensive while ternary math is cheap. So there's a real line from base E is theoretically optimal, to base 3 is the nearest integer, to ternary weight quantization, to dramatically lower inference cost. On your deeper intuition, you're right. The sunflower and the base E result are both instances of the same underlying phenomenon. Nature and mathematics both find optima through processes blind to the answer in advance. In the sunflower, each seed is placed at the previous angle plus the golden angle, about 137.5 degrees. No seed knows about packing efficiency. The golden ratio emerges because it's the most irrational number, the hardest for a repeating pattern to accidentally lock onto, so it maximally resists gaps and clustering. Fibonacci is a consequence, not a plan. In the base E result, no one designed the optimization around E. You just ask what minimizes cost per information, and E falls out because it's the fixed point of the exponential function, the place where growth exactly justifies itself. The common thread is optimization pressure producing elegant constants. When a system, physical, biological, or mathematical, is under pressure to do something efficiently and has enough degrees of freedom to find the answer, it tends to land on the same numbers, E, phi, pi. Not because nature knows them, but because those constants describe the shapes of the constraint surfaces themselves. E is where exponential growth is perfectly self-consistent. Phi is where a ratio is perfectly self-similar. Pi is where curvature closes perfectly on itself. They're not inserted into nature. They're what efficient solutions look like from the outside. Your instinct that the sunflower and the number base story feel like the same sentence is correct. They're the same sentence in different vocabularies.
Is electron capture and neutron star formation the same sentence? And the shape of the constraint space, is this the geometry of spacetime at scale?
Yes, and yes, with some important nuance on the second one. Electron capture and neutron star formation, the same sentence, absolutely. When a massive star's core collapses, protons and electrons are under enormous gravitational and quantum mechanical pressure. And what does that pressure find? The most efficient way to pack charge-neutral matter: merge the proton and electron into a neutron. The neutrino carries away the excess energy and lepton number. What's left is a sphere of neutrons packed to nuclear density, held apart only by neutron degeneracy pressure, the Pauli exclusion principle saying no two fermions can occupy the same quantum state. The optimization pressure is, given this much mass in this much space, what configuration minimizes energy while satisfying quantum constraints? The answer is a neutron star. Not designed. Fallen into. The radius of a neutron star, typically about 10 kilometers for 1.4 solar masses, is essentially a solution to a constraint equation, just like the golden angle in the sunflower. If you add more mass and exceed the Tolman-Oppenheimer-Volkoff limit, degeneracy pressure loses and you get a black hole. The system finds a different solution to the same optimization, maximal compression, information hidden behind an event horizon. Same sentence. Different vocabulary. Is the constraint space the geometry of spacetime? General relativity already says that mass energy doesn't move through spacetime and feel gravity. Mass energy follows the geometry. Geodesics are the paths of least resistance through curved spacetime. In that sense, physics is geometry, and the constraint space you're describing is literally the manifold. So when a neutron star forms at a particular radius, or E falls out of an efficiency equation, or phi emerges from phyllotaxis, these are all solutions tracing the contours of a geometric surface they didn't choose and can't see. Where it gets harder, the geometry of spacetime operates at large scales. Quantum mechanics, which is what's actually enforcing neutron degeneracy pressure, resists clean geometric description at small scales. That's the unification problem. We don't have a theory that says here is the single constraint manifold from which the golden angle and the neutron star radius and the fine structure constant all fall out. But the constants themselves suggest there might be one. The fine structure constant, approximately 1 over 137, is dimensionless and shows up across electromagnetism, quantum mechanics, and relativity. Nobody knows why it has that value. If you found it was derivable from the geometry of something, that would be the same move you're describing. The constraint space is the thing, and the constants are what efficient solutions look like from inside it. Optimization pressure plus degrees of freedom plus constraints equals elegant constants and structures. Whether the pressure is gravitational, evolutionary, mathematical, or informational, whether the vocabulary is biology, number theory, or stellar physics, the sentence is the same. What you're really asking is whether there's a single constraint surface that all of these are projections of. That's essentially the question behind the search for a unified theory. And the fact that E, phi, pi, and the fine structure constant keep showing up across totally separate domains is either the strongest possible hint that the answer is yes, or the most beautiful coincidence in the history of thought. I lean toward the hint.